Welcome to this video. The topic for today's video is the objectives used in microscopy. So, dear learners, let us begin with the learning objective and what this particular topic would be dealing with. When we speak about the objectives and their role in microscopy, they play a tremendous role, especially when we try to observe a specimen. So depending upon the purpose and the importance of different types of the objective lenses in microscopy, we can have different approaches. So the topic of objectives used in microscopy plays the basic important role, especially for observing the specimens at microscopic dimension. So let us see the learning objectives for this video. To describe the different types of objectives, to illustrate the role of oil immersion objective used in microscopy with a diagram, and to elaborate on the resolution of a microscope. So before moving on further, let us see the different types of objectives used in microscopy. This table has been taken from the book Microbiology by Prescott, 5th edition. So this particular table has the columns. The first column is about the property, different aspects which we consider for the property of a particular objective, and the different columns are for scanning, low power, high power, and the oil immersion. When you speak about the magnification for scanning is 4x, that means 4 times magnified. For low power 10x, for high power 45x, and for oil immersion 90 to 100x. Numerical aperture which we had discussed in the last video. So for the numerical aperture, it is 0.10 for scanning, 0.25 for low power, 0.55 to 0.65 for high power, and 1.25 so 1.4. So you can see it is relatively higher for oil immersion. And we had a separate video. So I believe you all have seen that video on numerical aperture and how it can be raised. The approximate focal length, it is 40 millimeter for scanning, 16 millimeter for low power, 4 millimeter for high power, and 1.8 to 2 millimeter for oil immersion. The working distance, we shall be discussing more of this in the coming part of this video. So 17 to 20 millimeter for scanning, 4 to 8 millimeter for the low power, 0.5 to 0.7 millimeter for high power, and 0.1 millimeter for oil immersion. And the next part is for the approximate resolving power if you're using blue light. So you can see for scanning 2.3 micrometer, 0.9 micrometer for low power, 0.35 for high power, and 0.18 for the oil immersion. So dear students, if you remember the previous video where I had discussed about the numerical aperture. So the last part of that, we had discussed that the only practical solution in order to have a higher and a better resolution is to increase the numerical aperture. And there we had discussed about the role of oil. So in this particular picture, you can see what would happen if there is oil and what would be the case if there is no oil. If you focus on this diagram, you yourself can make out the difference. When there is no oil, there is a greater possibility for the loss of light by the reflection, refraction. So the practical solution is to have oil so that there will not be loss of the light rays and they will be passing through. So basically the oil is working as an additional lens. So the oil plays a very important role, and this will be very helpful so as to have a better, higher resolution. Now when you speak about the resolution of complete microscope, the resolution of a microscope depends upon the numerical aperture of its condenser as well as the objective. And this is very clear from this equation which you can see on the screen, describing the resolution of a complete microscope. So D microscope is equal to the D microscope equals to wavelength divided by the numerical aperture of the objective plus the numerical aperture of the condenser. Now most of the microscopes, when we have in the routine field, they focus on the particular aspect of values where you need to focus on different terms So most of the microscopes have a condenser with a numerical aperture between 1.2 and 1.4. So however, the condenser numerical aperture will not be much more than 0.9. But this can be the case unless the top of condenser is oiled with the bottom of slide. So during the routine microscope use, the condenser usually is not oiled, and this will limit the overall resolution. The limits which are set on the resolution of a microscope, basically, it can be calculated using the equation. So you can see in this screen, using the AB equation, we can calculate the limits set on resolution of a light microscope. The maximum theoretical resolving power of a microscope with an oil immersion objective, numerical aperture 1.25, and the blue-green light is this way calculated. So we have the product of 0.5 multiplied by 530 nanometer and divided by 1.25, and that is how we get this particular image and the resolution in the case of a light microscope. So dear students, in this video we had discussed about the importance, how the numerical aperture could be. So just to summarize, at best, a bright field microscope can distinguish between two dots, which is around 0.2 micrometer. They are 0.2 micrometer at a distance from each other, the same size as a very small bacterium. So this is how we can calculate the limits set on a resolution of a light microscope. So thank you for listening and keep exploring the world of many wonders. We shall be discussing more of the further parameters in the coming video. Thank you.